Welcome people! Today we're going to learn Laplace Transform. By the end of this video, you'll understand where does this formula come from. The key to understand Laplace Transform is understanding the power series. Power series take a discrete function a of n multiplied by x to the n and then spit out a new function a of x, capital A of x. It's usually denoted as a sub n, but I'm going to write it in function notation in this video, a of n, to emphasize that it's a function. So, let's look at an example of power series. In this example, where the function is 1, a constant function, our infinite sum is x to the n. And this is equal to 1 over 1 minus x when x is in between minus 1 and 1. We inputted a function of n, which is a constant function in this case, and we got out a function of x. So we change the variable. It's kind of like a transform, as you may think. Let's look at another example. In this example, my point is more clear. We input a function of n, 1 over n factorial, and we get out a function of x, e to the x, which is so x to the n divided by n factorial is the Taylor series expansion of e to the x. So think of it as we multiply 1 over n factorial with x to the n. Our a of n is equal to 1 over n factorial, and we get e to the x. So we give this power series a function of n, and we wanted to multiply this n with the x to the n, and then sum it up until infinity, and forever sum it up over and over, and it converges to a value. It converges e to the x. So we transformed our function, and this is what Laplace transform is all about. But in Laplace transform, the function we give is not a discrete function like a of n. A of n is discrete and can be 0, 1, 2, 3, 4, 5. It can be natural numbers. But in Laplace transform, it can be all real numbers. So it's going to be a continuous function. And we're going to look what happens to this continuous function when we sum it all up. And summing up continuous values is integrating. Now let's go back to our original formula for the power series to make it into a continuous sum using an integral. And now we're not going to deal with a discrete function like f. We're going to deal with a continuous function f of t. And let's integrate this function from 0 to infinity to sum it all up for all real numbers. But we are not done. We need to multiply this with a power term like x to the n, but in this case it is x to the t. It's x to the t dt. And this is Laplace transform, but we are not done. This is problematic. We have t, which is the variable we are integrating over, in the exponent, and the base is x, which is just a constant for this integral. We're going to deal this x as if it's a constant and get a function of x in the end. But we need to change this because we don't like bases other than e. So let's write x to the t in the e base. X to the t, actually x is equal to e to the ln x, because they cancel out each other and we just get x. So then x to the t is equal to e to the ln x to the t, which is just e to the t ln x, e to the t ln x. Now I'm going to do something that will make my job easier to apply Laplace transform. I will introduce a new variable s and say that this is equal to minus ln x. When I introduce this new variable, I say that this s is equal to, I write s in x terms, and then I will substitute this into my integral, and my result of the integral will not be in x terms, it will be in s terms. And that's why you saw an s in the beginning of the video, in the formula. We're not going to deal with x. X doesn't matter in this formula. In this formula, t matters. The output variable x is just a name for the variable. So I'm going to change it to minus lnx, and this is going to be equal to e to the minus st. So if I substitute this into the integral, I get, so x to the t is equal to e to the minus st. E to the minus st dt, and this is Laplace transform. This is a complete Laplace transform. This is the complete formula, and now you know why. Now you know why we have a minus st term here. And the reason why I wrote minus lnx instead of lnx, if I wrote st, so if I said this is equal to lnx, this would be just st, and then s needed to be negative for this integral to converge. I don't want to deal with a negative output, so I said that s is equal to negative lnx. And you can deduce that lnx will be negative by itself, because x here should be in between minus 1 and 1. We saw that why in the power series. So now lnx, if x is a fraction, is smaller than 1, then lnx is a negative number, so because the natural log of fractions is negative. So we negate that again to get a positive x, and we put the minus sign here for this integral to converge. And this is Laplace transform. In the next video, we're going to apply Laplace transform on some functions. See you then.